In this video, we're learning how to take the derivative of a linear combination of two functions. So I've given this the name capital L, standing for linear combination, and that's a times f of x plus b times g of x, where a and b are just constants. In other words, a linear combination is a sum of constant multiples of functions. Now I want to point out that practically every calculus textbook actually states this one property as three different rules. You'll get one rule for how the derivative acts over a sum of two functions, one for a difference, and one for a constant multiple. But those are all special cases of the idea of the derivative of a linear combination. For example, if we set a and b both equal to 1, then our linear combination is just the sum of f of x and g of x. If we set a equal to 1 and b to negative 1, then our linear combination is the difference of the two functions, f of x minus g of x. And if we set b equal to 0, then our linear combination reduces to just a constant multiple of f of x. So if we can prove how the derivative works over a linear combination, we've automatically proven how it works for sums, differences, and constant multiples of functions. So I really have two motivations for teaching it this way. First, I'd like to have the shortest list of rules possible. And if I can use one rule instead of three, that's a good thing. Secondly, the idea of linear combinations is a really important idea that's sprinkled all over in the world of mathematics, and we may as well just start talking about it frankly right now. So to figure out how derivatives work over linear combinations, we have to go back to the limit definition of the derivative. So L prime of x, in other words, the derivative of the linear combination, is the limit as h goes to 0 of L of x plus h minus L of x, all divided by h. And I'll post a link at the top to the video where I first derived this limit definition of the derivative. So L of x plus h just means you take your original function L and replace all the x's with x plus h's. So that's going to give me a f of x plus h plus b g of x plus h. Then I have to subtract from that L of x. And L of x is just a f of x plus b g of x. Now, when we use the limit definition of the derivative to prove general properties about the derivative, the whole game we're playing here algebraically is that we want to recognize the derivative of individual functions hiding in this limit. So what I'm looking at immediately is that I have an f of x plus h here, and if I could get a minus f of x next to that, well, that would start to look a lot like the derivative of f. And fortunately, there is a minus f of x hanging out over here. So we're going to distribute the minus sign across this second term. And then again, I want to gather the f containing terms together, and I'm trying to find the derivative of f in this expression. It's already really close. I'll do the same thing for the g containing terms. So I have a b g of x plus h minus b g of x. And at this point, you may just see how to get to the final answer, but I'm going to throw in just a couple more steps of algebra. The first thing I want to do is use the fact that if I have a sum of two things up there in the numerator and then I divide by h, I can write it as two separate fractions. I can write it as the first piece divided by h plus the second piece divided by h. And now in the next step, I'll do a couple things at the same time. First, the limit of a sum of two things is equal to the sum of the limits. In other words, I can break this into two separate limits, one for the f containing terms and one for the g containing terms. Secondly, I can factor an a out of the first one, and I can factor a b out of the second one. And this, of course, is the moment we've been waiting for. I've now isolated the derivative of f in my first limit. That's literally just the definition of the derivative of f. So there's f prime of x. And my second limit is g prime of x. So we arrive at our conclusion here. When I take the derivative of this linear combination, all I have to do is just take the derivatives of the individual functions that are in the linear combination. So to write down our general rule, it's actually handy to use a combination of Leibniz notation and Newton's prime notation. So I'm going to say the derivative of a f of x plus b g of x. And that's the Leibniz notation for the derivative there, where I write d dx, and it means take the derivative of this thing. This turns out to be a f prime of x plus b g prime of x. In other words, the linear combination of the derivatives. So this is one case where derivatives behave in the simplest possible way. If you take the derivative of a linear combination, you get the linear combination of the derivative of the individual functions. Now I want to point out that in the previous video, we figured out how to differentiate power functions. In other words, functions of the form x to the n. And now we know how to differentiate linear combinations. And this means we can start differentiating linear combinations of power functions. But that's exactly what a polynomial is. So at this point, we're able to handle any polynomial without having to go back to the limit definition of the derivative. So we have a couple quick examples here, and we're using Leibniz notation in one of them and prime notation in the other, just to keep practicing both of these things. And I'm going to continue to show more steps than I actually do in real life, just because we're so new at this. If I take the derivative of this first one, 2x squared plus 3x minus 5, what we just found out is we just take the linear combination of the derivatives. So to really expand this and take our time, my first term is going to be 2 times the derivative of x squared. My second term is going to be 3 times the derivative of x. In my third term, you have a couple options here. You could call this negative 5 times the derivative of 1. There's a factor of 1 implicitly there. Or you could just say minus the derivative of 5. Or you could even say plus the derivative of negative 5. No matter how you write that last term, you're going to get 0 out of it because the derivative of a constant is 0. For the other two terms, we apply the power rule derived in the previous video. So the derivative of x squared, you bring the power down in front, subtract 1 from the existing power. So I end up with a 2x. For the derivative of x, I bring the power of 1 down in front, subtract 1 from the existing power. So that gives me 1x to the 0, which is just 1. And again, the derivative of a constant over in that third term vanished already. So we clean things up and write a final answer down. I end up with 4x plus 3. Now I do want to point out what this should look like as you become more fluent with taking derivatives. You want to get to the point where you can just quickly go through this list of terms in your polynomial. And you look at the first one, that's a 2x squared, and you go, okay, the derivative of x squared is 2x. And 2 times 2x is 4x. And then my second term, 3 times the derivative of x, but the derivative of x is just 1, so I end up with a plus 3. And then the derivative of a constant, of course, is 0, so I don't have to worry about that. So these really are just a one-step problem once you've gotten enough practice. In our next example, we're told we have a function f of x equals 5 minus 4x cubed plus x to the 5th, and we want to find f prime of x, in other words, find the derivative. So I go down the list of terms, and it starts with a 5, which is a constant. So I know that's going to differentiate to 0. I'm not even concerned with that. Then I get a minus 4 times the derivative of x cubed. And using the power rule on that, I bring the exponent down in front. That's a 3. And then I subtract 1 from the existing exponent, and this gives me 3x squared. In my next term, applying the power rule again, the derivative of x to the 5th is 5x to the 4th. All we have to do is clean up the 4 times 3 here, and I end up with a negative 12x squared plus 5x to the 4th, and we're done with that one. In the next video, we learn how to compute the derivative of a product of two functions. So two functions multiplied together, and unlike this linear combination case, the behavior of the derivative is not simple or intuitive over a product of two functions. I'll post a link to that video at the upper left. And I've also posted a link to my derivative playlist at the lower left, and I'll see you there.